How did the universe begin? Have you ever stood beneath a clear night sky, away from city lights, and just looked up? Thousands of stars scattered across the darkness, the band of the Milky Way stretching overhead, maybe even the faint smudge of the Andromeda Galaxy visible to your naked eye. It's a humbling sight, isn't it? Each of those distant points of light represents entire worlds, solar systems, galaxies, collections of matter and energy vast beyond comprehension. And yet, remarkably, all of it, every star, every planet, every galaxy, every atom in your body and mine, all of it had a beginning. This thought has captivated humanity since we first gazed skyward. Every culture throughout history has created origin stories to explain how everything began, from ancient creation myths to religious texts to philosophical ponderings. We've always been fascinated by that fundamental question. Where did all of this come from? Today we have something our ancestors didn't, the scientific method and powerful tools that allow us to peer back through cosmic time to the very edge of the beginning itself. We're going to explore what modern science tells us about how the universe began. But I need to warn you, what we're about to discuss will challenge your intuition. We'll encounter temperatures hot enough to melt subatomic particles, densities so extreme they defy comprehension, and timescales so brief they make a microsecond seem like eternity. We'll grapple with concepts that push against the very limits of human understanding. And here's the most exciting part. This isn't speculation or mythology. This is a scientific narrative backed by real observational evidence, mathematical models, and testable predictions. It's the most accurate picture we've ever had of our cosmic origins, though it remains incomplete in fascinating ways. So, join me for the next hour as we journey back to the very first moment of existence, when space, time, and reality as we know it burst into being. This is the story of how everything, literally everything, began. The Big Bang Theory. Basics. Let's start with the leading scientific explanation for how our universe began. The Big Bang Theory. But first, I need to clear up perhaps the most common misconception about it. Despite its name, the Big Bang wasn't an explosion in space. It was an expansion of space itself. About 13.8 billion years ago, all the matter and energy in our universe was compressed into an incredibly hot, dense state. Physicists often describe this as a singularity, a point of infinite density and temperature. Then, in a fraction of a second, this singularity began to expand and cool, eventually forming the universe we see today. Now, I need to be careful here. When I say all the matter and energy, I don't mean just the stars and galaxies we see today squeezed into a small space. I mean every subatomic particle, every photon of light, every quantum of energy, all of it concentrated in a region smaller than a single atom. In fact, in the earliest moments we can describe mathematically, the entire observable universe would have been smaller than a proton. To truly appreciate how revolutionary this idea was, we need to understand the historical context. For most of human history, the prevailing view was that the universe was eternal and unchanging. It had always existed and would always exist in roughly the same form. Even Einstein initially believed this, adding a cosmological constant to his equations of general relativity to ensure a static universe. But in the 1920s, evidence began to mount that the universe was not static after all. Let's explore the three major pillars of evidence that support the Big Bang Theory. Evidence 1. The expanding universe. The first breakthrough came from an American astronomer named Edwin Hubble. In the 1920s, Hubble was using the world's largest telescope at Mount Wilson Observatory to study distant nebulae. At that time, there was great debate about whether these nebulae were relatively small objects within our own Milky Way galaxy, or if they were actually island universes, entire galaxies in their own right, far beyond our own. Hubble resolved this debate by identifying individual stars within these nebulae and measuring their distances. He proved they were indeed separate galaxies, millions of light years away. But Hubble's most profound discovery was yet to come. By analyzing the light from these distant galaxies, he noticed something strange. Almost all of them showed a redshift in their spectral lines. Let me explain what that means. When a light source moves away from an observer, the wavelengths of light get stretched out, shifting toward the red end of the spectrum. It's similar to how the sound of a police siren drops in pitch as it speeds away from you. This is called the Doppler effect. What Hubble discovered was remarkable. Not only were galaxies moving away from us, but the farther away they were, the faster they were receding. This relationship became known as Hubble's law, and it suggested something profound. The entire universe is expanding. Imagine dots drawn on a balloon. As you inflate the balloon, every dot moves away from every other dot. The further apart the dots are initially, the faster they move apart as the balloon expands. This is exactly what we observe with galaxies. They're like dots on the surface of an expanding balloon, except in 3 dimensions. The implications of this discovery were revolutionary. If the universe is expanding today, then logically, it must have been smaller in the past. Rewind the cosmic film far enough, and everything converges to a single point. This was the first key evidence supporting what would later be called the Big Bang theory. Now, an important clarification. This expansion doesn't mean that we're at the center of the universe with everything moving away from us. From any galaxy in the universe, all other galaxies would appear to be moving away. There is no center to the expansion. Space itself is stretching everywhere. Let's take a moment to appreciate the magnitude of this discovery. By observing the motion of distant galaxies, Hubble had uncovered a fundamental truth about our universe. It has a history. It changes over time. It had a beginning. This completely transformed our cosmic perspective. Evidence 2. Cosmic microwave background. The second major piece of evidence for the Big Bang came decades later, and it was discovered entirely by accident. In 1964, 2 radio astronomers at Bell Laboratories named Arno Penzias and Robert Wilson were testing a highly sensitive microwave receiver. No matter where they pointed their antenna, they detected a persistent background noise, a faint microwave signal coming from all directions in space. At first, they thought this mysterious signal was caused by equipment malfunction or perhaps pigeon droppings in their antenna. They actually climbed inside to clean it out. But after eliminating all possible sources of interference, they realized they had stumbled upon something truly significant, a faint microwave glow permeating all of space. As it happened, just a few miles away at Princeton University, physicist Robert Dicke and his team had been specifically searching for exactly this radiation, which had been predicted years earlier as a consequence of the Big Bang theory. Here's why this discovery was so significant. If the universe had indeed begun in an extremely hot, dense state, then as it expanded and cooled, there would have been a point about 380,000 years after the Big Bang when the universe cooled enough for electrons to combine with nuclei, forming the first atoms. Before this moment, the universe was opaque, like a dense fog, because free electrons scattered photons of light. But once atoms formed, light could travel freely through space. This liberation of light is preserved as a kind of fossil radiation that has been traveling through space ever since. As the universe continued to expand, this radiation would have been stretched and cooled, eventually shifting from visible light to microwaves. This is exactly what Penzias and Wilson had discovered, the afterglow of the Big Bang itself. It became known as the Cosmic Microwave Background Radiation, or CMB. Think of it like this. Imagine you walk into a dark room and touch the walls. They're warm. You can't see the fire that heated them, but you know something hot was there. The CMB is like those warm walls. It's the leftover heat from the intense temperatures of the early universe. What makes the CMB such compelling evidence is its remarkable uniformity. It has almost exactly the same temperature in all directions, about 2.7 degrees above absolute zero. This uniformity supports the idea that the entire universe was once in a hot, dense state. But the CMB isn't perfectly uniform. In the 1990s, the COBE satellite detected tiny temperature fluctuations, variations of just 1 part in 100,000 that correspond to slight density differences in the early universe. These minute variations are the seeds from which all cosmic structure, galaxies, stars, planets, would eventually grow. Subsequent missions like WMAP and Planck have mapped these fluctuations with incredible precision. The patterns we observe match exactly what we would expect from quantum fluctuations in the early universe, amplified by a process called inflation, which we'll discuss shortly. The CMB is often described as the most perfect blackbody radiation ever measured, meaning its spectrum precisely matches what theory predicts for radiation in thermal equilibrium. This perfect match between theory and observation is one of the strongest pieces of evidence for the Big Bang. Evidence 3. Cosmic abundances. The third major pillar supporting the Big Bang theory comes from the abundance of light elements in the universe, particularly hydrogen, helium, and traces of lithium. According to the Big Bang theory, during the first few minutes after the Big Bang, conditions were hot and dense enough for nuclear fusion to occur throughout the universe. This brief period, called Big Bang nucleosynthesis, transformed some of the universe's hydrogen into helium and small amounts of other light elements. The theory makes very specific predictions about the proportions of these elements that should have been produced. About 75% of the universe's mass should be hydrogen, about 25% helium, and just trace amounts of deuterium, heavy hydrogen, lithium, and beryllium. When astronomers measure the abundance of these elements in very old stars and distant gas clouds, material that hasn't been processed inside stars, they find exactly these proportions. The match between prediction and observation is remarkably precise. To appreciate why this is such strong evidence, consider that stars also produce helium through nuclear fusion. But if all helium came from stars, we'd expect to see different amounts in different parts of the universe, depending on how many generations of stars had lived and died there. Instead, we see a consistent baseline amount of helium everywhere we look, exactly matching what the Big Bang theory predicts. The presence of deuterium is particularly significant. Deuterium is easily destroyed inside stars, but very difficult to create. The fact that we observe a specific amount of deuterium throughout the universe is a strong indicator that it was produced in the conditions of the early universe, just as the Big Bang theory predicts. What's especially compelling about this evidence is that the calculations for Big Bang nucleosynthesis were worked out before we had accurate measurements of primordial element abundances. When those measurements later became possible, they match the predictions beautifully. That's the hallmark of a powerful scientific theory, making predictions that are later confirmed by observation. Together, these three observations, the expanding universe, the cosmic microwave background, and the abundance of light elements, form the three pillars of the Big Bang theory. Each independently points to the same conclusion, and together they provide overwhelming evidence that our universe did indeed have a beginning, in an extremely hot, dense state about 13.8 billion years ago. Now that we've established the evidence for the Big Bang, let's journey through time to explore what happened in those earliest moments, as best we understand it today. The first moments. We're now going to travel back in time to explore the first moments after the Big Bang. And I mean the very first moments. What I'm about to describe happens faster than you can snap your fingers. In fact, much of it happens faster than light can cross the diameter of a proton. Before we dive in, I need to emphasize an important point. Our understanding becomes increasingly speculative as we approach the exact moment of the Big Bang itself. Our current theories work incredibly well, down to incredibly small fractions of a second after the beginning, but they break down completely at the exact starting point, what physicists call the Planck time, about 10 to the negative power of 43 seconds after the Big Bang. The Planck epoch. Time, 0 to 10 to the negative power of 43 seconds. At time 0, the exact moment of the Big Bang, our current laws of physics break down completely. We simply don't have the mathematical tools to describe what happens at this exact instant. The equations of general relativity, which describe gravity, and quantum mechanics, which govern subatomic particles, become mutually incompatible. We need a theory of quantum gravity to understand this era, and while there are promising candidates like string theory and loop quantum gravity, none have been experimentally verified. During this Planck epoch, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were presumably unified as a single force. The universe was smaller than a subatomic particle, yet contained all the energy and matter of today's observable universe. Temperature and density would have been essentially infinite. It's important to note that we don't know what caused the Big Bang, or what, if anything, came before it. These questions might not even be meaningful in the conventional sense, since time itself may have begun at this moment. This is a profound limit to our scientific understanding, and we'll return to these philosophical questions later. The Grand Unification. Epoch. Time, 10 to the negative power of 43 to 10 to the negative power of 36 seconds. As we move beyond the Planck time, our theories begin to gain some traction. During this era, gravity separated from the other three fundamental forces, which remained unified as a single electronuclear force. The universe was still inconceivably hot, around 10 to the power of 28 degrees Kelvin, and filled with a soup of energy and particles that would seem alien to us today. The laws of physics operated differently, and the kinds of particles that could exist were unlike anything in today's universe. The inflationary epoch. Time, 10 to the negative power of 36 to 10 to the negative power of 32 seconds. Now, we come to one of the most crucial periods in cosmic history, the inflationary epoch. During this brief window, the universe expanded exponentially, doubling in size at least 90 times in just a fraction of a second. This means the universe increased in volume by a factor of at least 10 to the power of 78. That's a 1 followed by 78 zeros. Wait, faster than light? Isn't that impossible? Not quite. Einstein's theory only says that nothing can travel through space faster than light, but space itself can expand however fast it wants. There's no speed limit on the expansion of space. Think of it like this. Imagine ants on a balloon. The ants, galaxies, can only crawl so fast on the surface, but if you rapidly inflate the balloon, space, the ants find themselves suddenly far apart without having moved quickly themselves. Cosmic inflation was proposed in the early 1980s by physicist Alan Guth to solve several puzzles about the early universe. First, why is the universe so flat? The CMB reveals that the universe is geometrically flat to a precision of 0.4%. Without inflation, this would be an extraordinary coincidence, but inflation naturally flattens the universe, just as inflating a balloon makes its surface appear increasingly flat at small scales. Second, why is the universe so uniform in all directions? Regions of the CMB on opposite sides of the sky were too far apart to have ever been in causal contact. They couldn't have exchanged information or energy, yet they have nearly identical temperatures. Inflation solves this horizon problem by explaining that these regions were actually in close contact before inflation and then were rapidly stretched apart. Third, where are all the exotic particles and monopoles that should have been produced in the early universe? Inflation dilutes their concentration to negligible levels, explaining their absence. The inflationary theory has made predictions that have been subsequently confirmed by observations of the CMB, including specific patterns in the temperature fluctuations. This gives us confidence that something like inflation really did happen, though the exact details remain an active area of research. The electro-wake epoch. Time, 10 to the negative power of 32 to 10 to the negative power of 12 seconds. After inflation, the universe continued to expand, though at a much slower rate. During this period, the strong nuclear force separated from the electro-weak force, the still unified electromagnetic and weak nuclear forces. The universe was filled with a hot quark-gluon plasma, a soup of fundamental particles moving at nearly the speed of light. This state of matter has been recreated in particle accelerators like the Large Hadron Collider, giving us a glimpse of what the early universe was like. The quark epoch. Time, 10 to the negative power of 12 to 10 to the negative power of 6 seconds. As the universe cooled to about 10 to the power of 15 degrees, the electromagnetic and weak nuclear forces separated, completing the division of the four fundamental forces as we know them today. During this epoch, quarks, the building blocks of protons and neutrons, roamed freely, unable to bind together due to the extreme temperatures. The universe was a superhot soup of quarks, antiquarks, gluons, electrons, photons, and other elementary particles, all colliding with each other constantly. The Hadron epoch. Time, 10 to the negative power of 6 to 1 second. About a millionth of a second after the Big Bang, the temperature had dropped enough, to about 10 to the power of 13 degrees, for quarks to bind together, forming hadrons, particles like protons and neutrons. This process is called hadronization. During this time, most matter and antimatter annihilated each other, converting their mass into pure energy according to Einstein's famous equation E equals mc squared. For reasons we still don't fully understand, there was a slight excess of matter over antimatter, about 1 part in a billion, which allowed some matter to survive. We'll revisit this mystery later. The Lepton epoch, time 1 to 10 seconds. By 1 second after the Big Bang, the universe had cooled to about 10 billion degrees, still incredibly hot, but cool enough for protons and neutrons to start forming the first atomic nuclei. Electrons and their antiparticles, positrons, dominated the universe during this period. As with matter and antimatter, most leptons and antileptons annihilated each other, leaving behind a small excess of electrons that would eventually combine with nuclei to form atoms. Nucleosynthesis, time 10 seconds to 20 minutes. Between about 10 seconds and 20 minutes after the Big Bang, conditions were just right for nuclear fusion to occur throughout the universe. Protons and neutrons fused together to form the nuclei of the lightest elements, mainly hydrogen, which is just a proton, helium, 2 protons and 2 neutrons, and traces of lithium. This process, called Big Bang nucleosynthesis, only lasted for about 17 minutes because the universe was expanding and cooling rapidly. Once the temperature dropped below about 1 billion degrees, fusion stopped, freezing in the elemental proportions we still observe today. Roughly 75% hydrogen, 25% helium, and trace amounts of other light elements. It's truly remarkable that in less than half an hour, the basic chemical composition of the universe was established. All heavier elements, carbon, oxygen, iron, gold, and so on, would have to wait for stars to form hundreds of millions of years later. The recombination, era, time, 380,000 years. For the next several 100,000 years, the universe continued to expand and cool, but remained a hot, opaque plasma. Light couldn't travel far before being scattered by free electrons, similar to how light is scattered in a dense fog. Then, about 380,000 years after the Big Bang, a crucial milestone was reached. The temperature dropped to about 3,000 degrees Kelvin, cool enough for electrons to bind with nuclei, forming the first complete atoms. This process is somewhat misleadingly called recombination, even though it was the first time atoms had combined. This was a transformative moment. Suddenly, the universe became transparent. Photons, no longer constantly scattered by free electrons, could travel freely through space for the first time. These are the very photons we observe today as the cosmic microwave background radiation, the oldest light in the universe. If we could have seen the universe at this moment, it would have glowed red hot in all directions. As space continued to expand over billions of years, these photons were stretched to longer wavelengths, cooling down until they now fall in the microwave portion of the spectrum. The Dark Ages and the first stars. After recombination, the universe entered a period called the Cosmic Dark Ages. With all the matter bound up in neutral hydrogen and helium atoms, and the initial fireball radiation shifted to longer wavelengths, there were no new sources of visible light. The universe would have appeared completely dark to human eyes. This period lasted for hundreds of millions of years. During this time, gravity slowly amplified the tiny density fluctuations that had been imprinted by quantum processes during inflation. Regions with slightly more matter exerted slightly stronger gravitational pulls, drawing in surrounding material and becoming even denser. Eventually, about 100 to 200 million years after the Big Bang, these concentrations of gas became dense and hot enough to trigger nuclear fusion, and the first stars were born. Astronomers call these population 3 stars, and they were unlike any stars in today's universe, extremely massive, bright, and composed only of hydrogen and helium. These first stars produced intense ultraviolet radiation that began to ionize the surrounding neutral hydrogen, creating bubbles of ionized gas that gradually grew and merged. This process, called reionization, transformed the universe from a dark neutral state back into an ionized plasma. But unlike the early plasma, this one was much less dense and allowed light to travel freely. The first stars lived fast and died young, many ending their lives in spectacular supernova explosions. These explosions scattered the first heavy elements, carbon, oxygen, and other elements essential for life, into space, enriching the gas from which subsequent generations of stars would form. Around this same time, the first galaxies began to assemble, as gravity drew collections of stars, gas, and dark matter into larger structures. Alternative theories. While the Big Bang theory has overwhelming evidence supporting it, science always leaves room for alternatives and refinements. Let's look at some other ideas about how our universe might have begun or what might have happened before the Big Bang. The Big Bounce. Some theoretical physicists propose the Big Bounce theory, suggesting our universe didn't begin from a singularity, but from the collapse of a previous universe. In this view, universes expand and contract in an endless cycle of big bangs and big crunches. The mathematics of loop quantum gravity, one approach to quantum gravity, suggests that as a contracting universe reaches a certain density, quantum gravitational effects would cause it to bounce rather than collapse to a singularity. This would avoid the problem of the laws of physics breaking down at the beginning. Evidence for a big bounce might be found in the CMB or gravitational wave background. The steady-state theory. The steady-state theory was a major competitor to the Big Bang in the mid-20th century. Proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi, it suggested that the universe has always existed and will always exist in roughly the same form. To account for the observed expansion, the theory proposed that new matter is continuously created throughout space, maintaining a constant average density. This satisfied what they called the perfect cosmological principle, the idea that the universe looks essentially the same at all places and times. The discovery of the CMB in 1964 dealt with this theory a fatal blow, as the steady-state model couldn't explain this relic radiation from a hot, dense past. Further observations of galaxy evolution over cosmic time have confirmed that the universe does indeed change significantly over billions of years. Multiverse theories. More recent theoretical developments suggest our universe might be just one of many in a vast multiverse. There are several variations of multiverse theories. In the inflationary multiverse model, cosmic inflation continues eternally in most regions of space, while occasionally forming bubble universes where inflation stops. Our universe would be one such bubble. String theory suggests a landscape of possible universes with different physical constants and laws, potentially realized in different regions of a higher dimensional space. The many worlds interpretation of quantum mechanics proposes that every quantum possibility is realized in a separate branch of reality, creating countless parallel universes. While fascinating, these multiverse theories are currently difficult or impossible to test experimentally, placing them at the boundary between physics and metaphysics. Brain cosmology. Another exotic idea comes from string theory's extension called M-theory. It suggests our universe exists as a three-dimensional brain, membrane, within a higher dimensional space. The Big Bang might have resulted from a collision between our brain and another. These alternative theories remind us that while the Big Bang model is extraordinarily well supported, our understanding continues to evolve. Science proceeds by constantly testing and refining its models against new observations and experiments. Current mysteries. Despite all we've learned, the birth of the universe holds many unsolved mysteries. Let's explore some of the biggest questions that still puzzle cosmologists. What caused the Big Bang? Our physics breaks down at the exact moment of the Big Bang, leaving us unable to determine what triggered it, or what, if anything, came before. Some physicists suggest the question itself might be meaningless, as time may have begun at that moment. Others propose various speculative ideas: quantum fluctuations, previous universes, or higher dimensional phenomena. What drove cosmic inflation? While evidence strongly suggests that cosmic inflation occurred, we don't know what cosmic force caused it. Theoretical physicists have proposed various inflaton fields that might have driven this exponential expansion, but none have been experimentally confirmed. The energy scale at which inflation occurred may have been beyond what our particle accelerators can directly probe, making it challenging to test these theories. Where is all the antimatter? The laws of physics suggest equal amounts of matter, and antimatter should have been created in the Big Bang. When matter and antimatter meet, they annihilate each other, converting their mass to energy. If exact equal amounts had been created, they would have completely annihilated, leaving a universe filled only with radiation, no stars, planets, or people. The fact that we exist proves there must have been slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. This asymmetry is called baryogenesis, and explains it remains one of the biggest challenges in cosmology and particle physics. In the 1960s, physicist Andrei Sakharov outlined 3 conditions necessary for baryogenesis, and various theoretical models have been proposed. Some involve processes in the very early universe that slightly favored matter over antimatter. Testing these models is a major goal of particle physics experiments: dark matter and dark energy. Perhaps the most perplexing questions involve dark matter and dark energy, mysterious components making up about 95% of the universe's contents. Regular atomic matter, the stuff we can see and interact with, accounts for just 5% of the cosmic inventory. Dark matter provides the gravitational glue holding galaxies together and shaping the large-scale structure of the universe. We see its gravitational effects, but it doesn't interact with light or regular matter in any significant way. Leading candidates include various exotic particles, predicted by extensions to the standard model of particle physics. Dark energy is even more mysterious, a form of energy permeating all of space and driving the accelerated expansion of the universe. Discovered in 1998 through observations of distant supernovae, dark energy might be a property of space itself, a new field, or a sign that our theory of gravity needs modification at cosmic scales. Together, dark matter and dark energy represent huge gaps in our understanding of the universe's composition and evolution. They remind us that despite our progress, we still don't know what most of the universe is made of: the horizon and flatness problems. While inflation provides elegant solutions to the horizon and flatness problems I mentioned earlier, we still don't fully understand the physics behind inflation itself. What field drove it? Why did it start and stop when it did? How did quantum fluctuations during inflation get converted into the large-scale structure we see today? The Hubble tension. One of the most intriguing recent developments in cosmology is the Hubble tension, a discrepancy between different measurements of how fast the universe is expanding. Measurements based on the cosmic microwave background give a slower expansion rate than direct measurements using supernovae and other standard candles. This discrepancy might point to new physics beyond our current models, perhaps new particles, modified gravity, or phenomena in the early universe we haven't accounted for. Frontiers of research. Some of the most exciting research in cosmology today focuses on pushing back the frontiers of our knowledge about cosmic origins. Let's look at a few key areas where scientists are making progress. The James Webb Space Telescope, launched in December 2021, is revolutionizing our view of the early universe. With its unprecedented infrared sensitivity, Webb can peer through cosmic dust to observe the first galaxies forming just a few 100 million years after the Big Bang. These observations help constrain our models of how structure formed in the early universe. In October 2023, Webb detected what may be some of the earliest galaxies ever observed, dating to just 250 million years after the Big Bang. Surprisingly, some of these early galaxies appear more massive and mature than our models predicted, potentially forcing us to revise our understanding of early galaxy formation. On the ground, experiments like the South Pole Telescope and the Atacama Cosmology Telescope are mapping the cosmic microwave background with unprecedented precision. These observations help constrain cosmological parameters and test models of cosmic inflation. Meanwhile, gravitational wave observatories like LIGO and Virgo have opened an entirely new window on the universe. By detecting ripples in space-time from cataclysmic events like black hole mergers, they provide a completely independent way to probe the cosmos. Future space-based gravitational wave detectors like LISA might even detect echoes from the early universe itself. At the smallest scales, particle accelerators like the Large Hadron Collider continue to probe the fundamental physics that governed the earliest moments after the Big Bang. The discovery of the Higgs boson in 2012 filled in a crucial piece of the Standard Model puzzle. But many questions remain. Future higher energy colliders may help answer questions about antimatter, dark matter, and the physics of inflation. Theoretical physicists continue to develop and refine models that might explain cosmic inflation, the nature of dark energy, and what happened at the exact moment of the Big Bang. Ideas from string theory, loop quantum gravity, and other approaches to quantum gravity are being developed, though experimental tests remain challenging. Perhaps most exciting is the prospect of detecting the cosmic gravitational wave background, ripples in space-time from the inflationary epoch itself. Several experiments are searching for the subtle imprint these primordial gravitational waves would leave on the polarization of the cosmic microwave background. These diverse lines of evidence, from the largest cosmic scales to the smallest subatomic particles, continue to refine and extend our understanding of how the universe began and evolved. Each new telescope, satellite, and experiment brings us closer to answering the deepest questions about our cosmic origins. Philosophical implications. The scientific story of cosmic origins raises profound philosophical questions that have fascinated humanity for millennia. Let's explore some of these deeper implications. First, there's the question of beginnings. If the universe had a beginning in the Big Bang, what caused it? Science describes how the universe evolved from its earliest accessible moments, but reaches a limit at the Planck time. Beyond that, our current theories cannot go. This limitation has sometimes been seen as leaving room for religious or philosophical interpretations of an ultimate cause. Others suggest that quantum cosmology might eventually explain how universes can arise spontaneously from nothing through quantum fluctuations. The philosopher Immanuel Kant identified this as an antinomy of pure reason. When we think about the ultimate origin of reality, we face equally puzzling options. Either an infinite regression of causes, which seems unsatisfying, or an uncaused first cause, which seems logically problematic. Then there's the question of fine-tuning. The laws and constants of physics appear calibrated with remarkable precision to allow for complex structures like stars, planets, and ultimately life. Change these values slightly, and stars wouldn't form, chemistry wouldn't work, and life as we know it would be impossible. Some see this apparent fine-tuning as evidence for a purposeful designer. Others point to the possibility of a multiverse. If there are countless universes with different physical laws, we naturally find ourselves in one compatible with our existence. This is called the anthropic principle. We observe a universe compatible with our existence because we could only exist in such a universe to observe it. There's also the matter of emergence and complexity. From remarkably simple initial conditions and basic physical laws, the universe has generated extraordinary complexity: stars, planets, ecosystems, brains, consciousness, culture. This emergent complexity suggests there may be principles of organization that transcend the merely physical, not supernatural, but perhaps not fully reducible to particle physics either. Finally, there's the question of meaning. Does understanding the universe's natural origins diminish or enhance our sense of wonder? Many scientists find that the scientific story, 13.8 billion years of cosmic evolution leading to creatures capable of comprehending that very story, is more awe-inspiring than any myth or legend. As Carl Sagan beautifully put it, we are a way for the cosmos to know itself. We are made of star stuff, assembled by natural processes into beings capable of contemplating our origins and place in the universe. These philosophical questions remind us that science and philosophy, far from being opposed, are complementary approaches to understanding reality. Science tells us how the universe works. Philosophy helps us reflect on what it all means. Conclusion. As we reach the end of our cosmic journey, let's step back and consider what we've learned about the beginning of the universe. We've traced cosmic history from the first fraction of a second to the emergence of structure and complexity. We've seen how a hot, dense, virtually featureless beginning evolved into the rich tapestry of galaxies, stars, planets, and life that we observe today. And we've explored both what we know with confidence and what remains mysterious. The Big Bang Theory stands as one of humanity's greatest intellectual achievements, a comprehensive, evidence-based account of our cosmic origins. It's a theory that has been repeatedly tested and refined over nearly a century, incorporating new discoveries and observations into an ever more detailed picture. Yet, science is never complete. The story of cosmic origins continues to evolve as we develop new technologies, gather more data, and propose new theoretical frameworks. The mysteries we've discussed, the exact nature of inflation, the matter-antimatter asymmetry, dark matter, dark energy, and what happened at the very beginning represent exciting frontiers for future exploration. What's truly remarkable is that we, beings composed of atoms forged in stellar furnaces, can contemplate our cosmic origins at all. We are the universe becoming conscious of itself, telling its own story. The atoms in your body were once part of the stars that exploded billions of years ago. The elements that make up our planet were synthesized in cosmic processes set in motion by the Big Bang. The quest to understand our cosmic beginnings touches on the deepest questions of existence. Where did everything come from? Why is there something rather than nothing? What does it all mean? These questions unite science, philosophy, and the human spirit in a shared search for understanding. And the search continues. With each new telescope, each experiment, each theoretical breakthrough, we edge closer to answering these fundamental questions about our universe's birth. Now, I want to hear from you. Which aspect of the universe's beginning do you find most mind-blowing? Is it the incredible precision of the CMB measurements, the possibility of multiple universes, the fact that we're made of star stuff? Share your thoughts in the comments below. Before we end, I want to emphasize something important. Science is not just a collection of facts, but a method for understanding reality. The story of how we piece together our cosmic origins is itself remarkable, a testament to human curiosity, creativity, and our ability to decipher the universe's secrets through careful observation and logical reasoning. If you've enjoyed this cosmic journey, hit that subscribe button and join me next time when we'll explore another fascinating question about our universe. Until then, keep looking up and wondering about the greatest story ever told, the story of our cosmic origins.